Hi, today I will explain about my PhD dissertation work, and it's about computer vision and object tracking. All right, so let's go through my PhD dissertation slide. So the title of my dissertation is called Enhancing Real-Time Multi-Object Tracking Through the Prime Framework and LITE Paradigm. So the two words, prime and LITE, they are the contribution of the work. And what we do is we enhance real-time multi-object tracking. This is the common problem nowadays. And this work is done when I was doing my PhD at the Computer Vision Lab in a university. And the financial sponsors of the work is HumbleBeeAI and the INA University. And okay, so let's see the simple demo of what multi-object tracking is. If you see, simply it's assigning identities for objects, right? This man in the black jacket has okay, let's start again. So he has a purple box. That's his ID, the ID 2. But this can change when he is overlapped or occluded by other person, like in the one going on here. Okay, so here you can see this purple is changing when he passes through, right? Now it's blue. So this is the really key issue in the field. And because of this, we have huge R&D opportunity to contribute to community, right? The more we work and research on this field, the better we can solve the problems with AI and automation. For the executive summary, for those who have also technical background, the key contributions of the work is lightweight integrated tracking feature extraction. It's a novel approach I introduced during my PhD. And the Prime, it's a new evaluation framework which allows practitioners, I mean the real users or the industry experts to leverage between the research and the practice, right? Because many of the papers show really awesome tracking methods, but when you deploy for your problem, like a problem of focus, business problem, it doesn't work, right? So this is a whole idea, like let us introduce Prime, and through Prime, we know how to fit and which tracker, which factors and which trackers to pick for our business problem. So the content is, after introducing the problem and scope, I will talk about the background, why we need to solve this problem, and what kind of challenges we have in MOT, multi-object tracking, and what other people did. And then we introduce Prime, LITE, and then we show why Prime is, how we can use Prime, what Prime offers us. If I am a computer vision engineer, or if I am a researcher, I need to develop the new research algorithm for object tracking, or I need to deploy best tracking method for my problem. How should I choose, right? So in this discussion section, this will be covered. So officially, the object tracking is simply keeping the identity of the object. So this person is 3. So across frames, we should keep him as 3, right? The 3 is identity, but you can give him a name or other identities. But the task it should be consistent, and it should be spatially located. Like we should know where a person is. All right, and it should be consistent across frames. And one more important thing about object tracking is it allows us to make this kind of motion pass, because this car is tracked when he was here until he was here. And now we know the car's like a trajectory. Why do you think this is important? Because I will tell you, one of our startups, Ant Vision, it's a product which optimizes city traffics. And during city traffic, we have to know from which crossroad, from which road to which road the car has passed. Why we need to know? Because based on this, we optimize the traffic light, when it should be red, when it should be green, for which road we should give yield, for which road we should stop them. That way, we maximize the throughput through this crossroad for vehicles and the passengers at the same time. So that's why we need to know this like a trajectory of the objects. So this is why the tracking is really the core concept in video analytics and computer vision artificial intelligence. All right, but there are, of course, challenges like everywhere. Challenges, if you see this image, track can be missed, right? So here we have 3 tracks, but here one of the track is missing because it's occluded. That's why there is no way to locate it. But okay, after some time, the track has appeared here, this maybe blue jacket lady. But still, this is not same as here. Here, it was blue. Now it's the green color, meaning the identity is switched, IT switch problem, right? So another thing is, if you see persons here, like this person is passing, and the other person is visible here. There's a detection, but when he is passing, he occluded the other person, the behind, right? So this is another like a pass crossing or occlusion problem. Okay, so now we saw early on the demo video of tracking, and it was byte track. Here it's named a little bit different, but if you see the paper, it's a byte track here. So this is one of the leading tracker at the time of my PhD defense, right? Which is not far, maybe 6 months ago. So this work is one of the famously used and open source, because others, they don't have paper, we don't know their methodologies. But this open source work has a 56-point HOTA score. HOTA is like an accuracy score. The 100 is ideal, right? I will introduce later what HOTA is. So what that means for us is large room for growth in multi-object tracking. So if you are a researcher, you can work here. If you are an AI engineer, this is really where you should work on. Or if you are a business owner, you should pay good money for a computer vision engineer, because if he is good enough and if he makes a good improvement, he can increase your accuracy or optimization of your business. For example, one of the things we did for businesses at HumbleBeeAI is we increased the tracking and detection accuracy of catching burglary, right? Because if you don't track accurately, you catch less burglars. If you track accurately and detect accurately, you catch more stealing, more theft. So just by knowing, just by investing into R&D, you can optimize your vision analytics. So this is not a place to save money, I would say, because of this large room for growth. Otherwise people just use what's available, and it's not a good solution for the business owners. And if you are a researcher, for you, this is a good opportunity to do research and make new solutions for community, right? Because that's why we do research, right? Not to graduate PhD or not to get a professorship promotion, but to contribute to community. All right, so now about ReID. Now we are introducing a new concept. ReID is when we saw the kind of occlusion happens, right? Or when object disappears from the frame and reappears. We have to re-identify, right? How do we re-identify? For example, in the soccer, maybe this guy missed from the camera and then appeared again, right? We have to re-identify who he is and who he was before. How do we do it? Using the features. We compare the appearance features. We extract appearance features from previous frame and the current frame, and then we match them to each other, all right? And the important part is our work assumes ReID is needed, right? I'm not the one who is saying we have to use ReID. But what we are saying is many people are using ReID, and other researchers proposed ReID-based methodologies. What we are saying is ReID-based methodologies are not real-time. And our work LITE proposes real-time solution for ReID-based tracking. Okay, so here's how ReID-based tracking works on a high level. We have video sequence. Now some kind of CNN here detected objects, right? The localization, it's also called object localization. And then after some pre-processing, we are passing through another CNN network and extracting features, right? So two CNN networks, like two deep learning networks. And then so these are tracks, right? From our past, we were tracking those 6 objects, and we have 6 detections. We have to match which one is which, right? And then this kind of track pass will emerge, okay? And at each frame, we will see these kind of identities, right? The 6 tracking identities. Important part here is you need to use 2 CNNs for this task and for this task. This is a really important part. And there is really this kind of pre-processing cost. I mean, you cannot crop this and then put inside CNN because you have to resize. It should be same shape, right? For the model, because model expects the same shape. So this is time consuming because of the pre-processing stage. Now, okay, so the key problems. We have so many problems in the domain, as we discussed, but our focus, our scope here is hidden factors influencing emotive performance. Because, as I said, what's shown in the paper is not really the accuracy in your deployment scenario. Like maybe people showed like a 50%, 60%, or maybe 100% accuracy. But when you deploy, it's just catching 10% of the burglary, or maybe 10% of the accidents, or maybe it's just counting 10% of the shoplifting. So like how can we improve that, right? And we show there is some really important factors such as confidence threshold, input resolution, detector type. And if you control those, you can get 2 times, 5 times better output. This is what really this work shows, okay? And then we also develop LITE paradigm. We show how we develop this paradigm. Notice this is not the methodology, it's a paradigm, meaning it can be applied to any ReID enabled tracking and then improve the speed while maintaining the same accuracy. This is a really core. The accuracy stays the same. Okay, and of course, there is really challenges because when you integrate ReID features, you have the 2 CNNs now, and it will be really slow. And we solve that challenge in this work. Okay, and there is a disconnect between the research and the practical deployment, as we showed. But what is the key is we show how it's due to limited holistic evaluation. Like there is no holistic evaluation methodology for object tracking. That's why there is a gap between research and the practical scenario. All right. So now, another key problem is speed and accuracy. And let's talk about here this picture action detection. In this picture, what is important is this is from the work Argus++. It's a real-time, they try to be real-time object tracking. Oh, sorry. They try to be action detection for surveillance scenarios. Their job is to detect for example, the suspicious activities. Maybe the car drops some bag, or maybe 2 persons are fighting, maybe they are just working, maybe somebody came to your perimeter of your building and taking some pictures, acting suspiciously. So this is what Argus++ does. It will recognize action, it will detect actions. And but it involves multiple components, right? First, there is a video stream, and there is the object detection from that video stream, right? That this object should be detected. and then they should be tracked across frames, right? So this is showing the multiple frames. And then from those frames, the proposals are generated, right? The kind of a clip, potential activity, potential action clips. And those clips after that, like they will be classified, right? Like recognized what kind of action it is. So this is what the action detection is. My point here is object tracking controls kind of impacts the final outcome or final accuracy of action detection system, both in terms of speed and in terms of accuracy. This is what I'm trying to say here, because if this is accurate, all the rest are accurate. And if this is slow, the whole system will be slow, right? Because this is a block, the blocker. You have to pass through this, otherwise you cannot get the output here. This is one of the reasons. Originally, I was given by my PhD advisor to work on this action detection, actually. And then I realized like a huge problem was actually object tracking. Everyone is trying to improve action detection, but when you dig deeper, object tracking itself is not solved problem. So if you focus on object tracking and then just plug it in, you have a really much better action detection. So object tracking is the really founding block for many computer vision applications. In short, here is a related work. When we talk about ReID enabled tracking, we want to know if the methods, these tracking methods contain ReID capability, and if that ReID capability costs extra inference cost computing, and if it requires training, and if it's real time, right? Notably, these motion-based trackers, the motion and the ReID, motion are different, right? ReID has appearance features when they are associating the track and the potential detection. But the motion just uses previous trajectory and then assigns based on motion, this detection is belonging to track 1, track 2. Because of that, motion-based trackers are fast, real-time. They don't have appearance feature extraction stage, right? There is no separate CNN to extract appearance features. On the other hand, these ReID-enabled trackers cost extra inference, and they need to be trained, right? And they are not real-time. So this is a two trade-off. But there is an integrated world, and the integrated world says, for example, fair mode combines the two into one. And they kind of one CNN network, and they solve both the ReID and object detection, right? However, they require extra training. And unlike fair mode, LITE-based trackers do not require extra training. So this is really the practical aspect of LITE. So if we go a little deeper into fair mode, which is the only most relevant methodology to LITE, the LITE paradigm, basically it trains encoder-decoder for two objectives, right? So the loss function has to optimize for detection and re-identification at the same time. So like a re-identification is kind of this embeddings, right? It will extract this kind of feature vector for each crowd, each object, each person. So the good thing is it doesn't require extra training because they added into one. But the bad thing is it doesn't require not extra training, but extra compute. This is what I want to say here. Extra compute. Interesting how I passed until here. Okay, and then the bad side is there is no. It requires a target data set, but ours doesn't require any target data set to train, right? So another thing is it's too complex, because when you try to optimize for two loss function. It's really tricky, kind of. There has to be a lot of R&D to get that this kind of network to work for your problem case. Okay, so now we move on to experimental setting. when we do any kind of comparison or any kind of R&D, we need to know which method is good compared to, or which breed or which selection is good. But to do that, we need a reliable evaluation metric. Evaluations are always tricky because the ideal evaluation is actually difficult to get. That's why object tracking world was using MOTA and IDF so far. But MOTA and IDF has issues. Like this is what I try to explain here. It's not me, actually. The authors of HOTA, they explained here. Assume you have ground truth, 100 frames. And there is just one track, right? One person is in 100 frame long video. And tracker A is keeping track for 50 frames, right? So it keeps, it has a one track ID and like a successful for the 50% of the time initially. But tracker B detects the person 70% of the time, but it proposes two tracks, right? The track one, track two, but actually there's only one track. So this tracker B is making a mistake. It says two track. Tracker C says there's four tracks, but good thing is it's detecting all the time. So now question is, which tracker is better, right? Because one is tracking only 50% of the time, but it says there's one object, one track. The second says there's two track, but it's the detection is 70% of the time. This one is saying like four tracks, but the good thing is it detects across all video or all clip. So if you go to MOTA, it's more like a detection biased, right? They both try to combine actually, they give a final score, but MOTA is more like detection biased. That's why from 50%, it increases up to 97, sorry. If you see IDF, it decreases from 67 till 25%. Why? Because association is getting worse, right? Association would be maximum if there is only one track. But this is not only, here there's only one track, but association is not 100 because IDF is also considering detection component to evaluate. So that's where HOTA comes in. HOTA says, okay, the MOTA is not sufficient and IDF is not sufficient. What we do is we need to make a subcomponent, detection accuracy and association accuracy. And they should evaluate, they should measure exactly the detection accuracy. Here you see 50%, 70%, 100%, right? And this is meaningful, interpretable. And the association accuracy should do the same. And then HOTA will combine the two into one and like kind of overall evaluation score. So that's why HOTA is reliable and they prove mathematically it's a monatomic function. All right, so from now on, we use HOTA. Obviously, we provide the other metrics for evaluation, but we need a primary metric. HOTA is our primary metric of evaluation, right? Because we need to follow one metric in order to see which model is good. So now, second thing is dataset. Like dataset is another important aspect of machine learning research. As you know, because different datasets, different scenario, and tracking methodologies perform differently on different datasets. This is important because maybe somebody got 100% on MOT17, and their that method, which got 100% on MOT17, works like just 50% on MOT20. On the other hand, somebody who got 100% on MOT20 dataset, their methodology may get lesser than that. I mean, a really bad score on MOT17. This is really the case, actually, because dataset scenarios are different and the different trackers have different strengths. So, and as a practitioner, if I'm deploying the machine learning models or the object tracking methodologies for some other businesses, I need to know which one is good given the business context, right? We don't just fit the solution to the problem. We understand the problem first, and a customized solution for this problem. That's what we really do at HumbleBee, right? That we customize tailored solutions for businesses so that the business owners have an edge over others. All right, so that's why we evaluate on multiple data sets, and notably Person Pass 22 is from Amazon, recently released, and it has 98 videos sequences. Okay, so now let's talk about our novelty prime framework. To say it simply, like a prime optimizes how we see prime redefines what is tracking pipeline. So previously, this on the bottom, this blue region was treated as a tracking pipeline or the tracking component, but we are treating everything as tracking component. We are unifying it. This is important because when you unify, this allows us to see effect of different detectors and effect of different appearance feature extraction. And also it allows us to see how performance changes when we increase the input resolution or when we change some parameters of this methodologies, right? Because they itself have a lot of intrinsic factors, and when you modify that, the final result changes. So this is really important for practical applications. So to maybe elaborate it a little bit more, if you see this figure, this is a modified figure from this documentation. Initially, other literature considers this green box as tracking, right? So if you talk about deep sort tracker, this is what they consider as a tracking component. However, in our prime methodology, we unify and we see all pipeline as tracking pipeline. Of course, we don't say it as like a tracking component, but we say tracking pipeline. And rather than evaluating the partial tracking component, we have to evaluate whole tracking pipeline in order to know practical performance in terms of accuracy and speed. So this is what the whole idea of prime is, right? Why this is important? Because you can change a lot of parameters here inside YOLO or here inside appearance feature extraction, or maybe you can merge these two like we did in LITE, we will see later. And then you gain a lot of speed advantage because you, instead of 2 CNN, you made one CNN, one network. Okay, so now this will solve a lot of problems such as incomplete speed measurements after we propose prime. And it allows us to identify key influencing factors. What happens if the tracking scene is dense, right? Too many people. And what happens if we change the detector settings, like input resolution or the confidence threshold? And what happens if we like a pipeline resolution, if we change? Sorry, I think the pipeline, yeah, because almost the pipeline resolution and speed are actually almost the same. Let me just remove this part. Okay, so because pipeline resolution and input resolution are for the detector are almost same. Okay, so the key factors is the scene density and the detector settings. So now if we see speed measurement, because now because of prime, we treat whole pipeline and we can measure how the tracking pipelines work. And here different colors represent different trackers, right? 4 colors. And we did this for multiple input resolution, right? And we also manipulated the confidence threshold of object detection, because when you change the threshold, the whole system changes. And what it shows is because some people require certain FPS, the real speed for their system to work. But because we saw it in practice, right, at HumbleBee when we were working on client projects, a client himself wants to change some confidence threshold, and then they come to us their system became slow. Why it got slow? Because if you, for example, reduced confidence threshold, there will be more candidate detections, which means there will be more work for tracking to extract features and make a matching. That's why like a speed changes when you modify the confidence threshold or any other parameters, right? And same for input resolution. Obviously, when you change the resolution, the speed drops. This is what the Prime now allows us to see, the practical impact of these intrinsic components or the factors. More importantly, not only speed, but the accuracy of the system, how accurate it works, also changes, right? This changes, for example, this is a 320 resolution, and this is 640 resolution. It changes when you change the resolution, the performance changes. And this is almost true for all trackers, right? All trackers change. And another thing it shows is we cannot really rely on this kind of evaluation because what other previous work does is they were reporting at certain threshold, confidence threshold, and we didn't know which threshold it was. But this is biased because if you cut here, maybe this yellow is better than the blue tracker. But if you cut here, maybe blue is better, right? If you cut here, maybe again, yellow is better. But of course, this is just better with small percentage, but those small percentages are seen as improvement in the community if you see the multi-object tracking results. So to say it shortly, all trackers performance vary when you change confidence threshold of the detector, and it affects also by input resolution, all right? What kind of input resolution you have. Right, so another thing is it's scenario dependent. If you see here, it was like going like this, kind of curvy, right? I mean, it goes up and goes down. But here it's a little different, right? This is at certain threshold, maybe at certain resolution, maybe really large resolution, this is happening. But at lower resolution, the low confidence threshold is always better. And this is because the MOT20 has a smaller object scale compared to MOT17. Actually, the better way is to compare it into COCO, where the YOLO models detectors are trained on, right? So MOT17 is maybe close to COCO's object resolution, but the MOT20's objects, the scale of their objects are much smaller than where the detector is trained on, which is why the confidence thresholds are low. And when you increase a resolution, then they try to behave like normally because their object scale is now similar to MSCOCO, where the originally detector is trained on. Point here is scenario dependence, right? The factors, how they affect is also dependent on the scenario of the object, where we are tracking, what is our problem, right? So another thing is we have multiple variants of YOLO detector, and we wanted to see how it affects, and we wanted to see it in two different confidence thresholds, right? So notably, the byte track is not affected by confidence thresholds. If you see these two, they are very close to each other. And this makes sense because byte track intrinsically handles multiple confidence thresholds. What it says is every detection matters, tries to not ignore low confidence detections. That's why it is immune for change of confidence thresholds. However, if you see kind of a detector impact, initially nano is performing not so bad, but when you move to small, an architecture which is bigger than nano, its performance increases, right? But when you go down, when you go up to larger models, it's going down rather than increasing. What that means? That means bigger detection is not always better. If you increase detector, it's changing, right? And it's not same for all. If you see here, for strong sort, the smaller threshold and the larger detections are better. Larger detectors and the smaller threshold is actually better. So this is really this changes everything, because we cannot rely on single detector evaluation, and we cannot rely on single confidence threshold evaluation. This prime is kind of shedding light into what's possible and what kind of factors are affecting our final performance, which is HOTA score here. And this is true across multiple trackers, right? The sort, deep sort, and OC sort. You can move on. So, and we did, that was only two confidence thresholds. Now we did multiple confidence thresholds. And in order to visualize, we merged all trackers' HOTA score into one, right? Point here is, high-level message here is when you increase the detection, right? So detection is increasing. Nano is smallest, second smallest, medium, large, and extra large. And what you expect is when you use larger detector, you get a better result, because larger is more expensive, and it's like a MAP value on the COCO detection dataset is larger for large models. However, this is not the case with object tracking, right? As you can see, when you increase up to some point, yes, detectors are increasing, but after hitting some confidence threshold, this is not changing. And we have some insights during the slides why this is happening, because there is a density issue, and we have to see the confidence of the detected objects depends on the density of the object, density of the scenario, the scale of the object, and the other factors. But the main message we are trying to deliver here is factors matter, right? We cannot just black box and choose. And we have to see the things with the lens of prime, the proposed framework. You have to see if you didn't have prime, we wouldn't be evaluate the effect of detectors on final tracking performance, right? Because now, thanks to prime, it treats whole unified solution system as a single tracking pipeline. That's why we are able to measure these accuracies. All right, so now we introduce LITE. It's a novel paradigm in multi-object tracking. And before that, let's go through a little background. It's about the cost matrix. When you match appearance features, we need to match kind of a detection track detection pair, and we need to compute the cost, because we need to assign the smallest cost, right? For example, if we see this as a cost, because some other implementations see it as a similarity, but if you see it as cost, for T0, this detection 3 will be assigned. Oh, sorry, detection 2 will be assigned because it has a smallest cost. For track 1, let's see, maybe that detection 0 will be assigned, because the detection 2 is already assigned to T0, and although they have the same cost for track 1. And for track 2, detection 1 will be assigned. So this is how cost matrix works, and it will simply compute Euclidean distance between track and detection pairs. And now a little bit about overall system of simple, maybe conventional, popular tracker, deep sort. What deep sort does is it has a detection neural network, convolutional neural network, and gives us detections. And then there's a feature extraction convolutional neural network. We call it CNN, and the CNN extracts features. And then the similarities of those features computed with confirmed tracklets similarities, right? Because for previous frames, the system was already tracking object tracks, and they have appearance features. And we have to compare those with the detected candidates' appearance features in order to assign who's who, right? So if you see this blue as tracks and this yellow as detections, we compute cost and then assign who is closest to who, right? And then they will be considered as matched tracklets. and matched, they just go to be associated with other like all tracklets. But unmatched detections and tracks, they go through second stage where IOU, intersection over union distance, measures their cost matrix, right? Cost matrix is computed based on how much they overlap to each other, right? So it's kind of spatial overlap, the current current detection with previous track's spatial location. How much do they overlap? And then like they will be like a more kind of they will be merged with motion. So this is motion association, and this is the similarity association, like appearance feature association. So this is also called the ReID matching, ReID component. So, and then in the end, the associated tracklets will be obtained. Like this person is associated for this person from previous track, and that this is associated to this, like from previous track. So this is the background of a deep sort. And so more recent works are bot sort, if you see. So they have almost similar methodology to deep sort. They have this detection, and they have this appearance feature extraction. What they do is they do some modification here, how they merge their cost, like IOU and the ReID cost, how do they integrate these costs. So this is what they do, small update algorithmically, right? And that's how people have been working on in the domain in terms of ReID enabled tracking. And another example approach is deep OC sort. And what they do is they like change, first of all, how they handle the motion. They change some Kalman filter algorithms in order to improve, make the motion tracking a little bit more stable. And they introduce adaptive weighting. When matching, we have to give different weight for different candidate tracks. Because when I'm being tracked, I have multiple props candidates, and when detection comes, my next frame detection, and it makes a match, we have to not give same score for every match. We have to consider their confidence of the detections. This is what this adaptive weighting means. Because if I'm well visible, there will be more higher confidence, like objectness or personness confidence for my crop, right? Maybe sometimes when I'm, let's say, when I'm hidden or like this, there will be lesser confidence for this crop. And because of this, the adaptive weighting doesn't favor this kind of less confident tracks. And then dynamic appearance modeling is kind of you can see the formula here. So what it does is it will keep the most recent crop as a representation, but also it will get the the previous tracks, previous candidates, summarized information as well, and it will merge it and dynamically updates my candidate crop representation in order to match it visually, make an appearance similarity computation. All right, so in summary, general ReID based tracking involves two CNNs, right? First, goes through YOLO detection, and this is detected, and then goes through appearance modeling CNN, and this is the appearance features for these three detections. So this is what the ReID enabled architecture looks like in general. And the proposal of LITE proposes to make it into one. Can't we somehow use one network and implement LITE on top of that and obtain these representations from here as well, rather than having run two CNNs? Why this is important? Because if you run two CNNs, this CNN has to wait the result of this CNN. This is one. Second is there will be a lot of resizing and pre-processing, post-processing, because this expects the objects crops to be on the same size, right? And the second thing is the sequential, like in parallel computing, we try to avoid sequential processes. We try to make everything into parallel, because that way, when the NVIDIA GPUs improve, like we benefit from speed. Otherwise, we have to wait the output of this detection network in order to start running this appearance model network, right? So this is a simple idea. And the proposal, I mean, the kind of methodology is to somehow extract these features from here. This is the whole goal. How do we do that? Can we do that? And the second thing is, when we do that, does that work, right? We have to verify. And this is kind of figure which explains how we did that. And if you see this basic YOLO backbone, it has a convolutional layers, right? When you have the input resolution, input image of 1280, like and pass through this CNN, it will be downsized, and then there will be separate YOLO head module, and then it will output this kind of detections, all right, where each object is. And what we are saying is, okay, do that, and at the same time, get this activation map, right? This is activation map. So this is the resolution is reduced because this is coming from first CNN layer, and it was downsized. And from here, project this detection into this activation map and crop it, right? We just crop it. And it will be, there will be depths. Important thing is, okay, so this here, 100 and the 150 is correspond to this dimension of the box, right? The downscaled or projected dimensions. And 48 corresponds to this depths, right? That this is the map, activation map is 48 channel deep. So now what we can do is we need to have a, in order for this methodology to work, we need to have a fixed sized vector. So what we do is we just reduce these dimensions by averaging, and then get 48 dimensional vector. That is what this representation is, like a 48 dimensional vector. So now we got like appearance features. Now the question is, does it work, right? Now we have to check if it works. So we ran a couple of experiments for that. And when we found is, this is a motion and ReID based trackers. So these two tables, subtables are what we should focus on. If you see, HOTA score doesn't change, right? HOTA score here doesn't change. However, their FPS changes. And FPS changes in favor of LITE, right? Because as we just discussed, LITE tries to optimize the speed, tries to make the object tracking in real time, because the object tracking is subcomponent of many other vision applications. And if you make it faster, and other vision applications will be faster. So that's why we maintained the same accuracy, but obtained much higher speed, right? So now let's see, actually, let's skip this slide. This is more important. So this is LITE version, and this is the original version, right? This is just a visual show. It's difficult to evaluate visually, but it will give you some feel. Basically, in terms of numbers, or if you see it closely, they don't differ in terms of quality. But what they differ is speed, right? LITE is working much faster, and it will also save a lot of GPU power usage, and it will save a lot of extra GPU compute. All right. So this is also bot sort and the LITE bot sort. So the basic idea is LITE is a paradigm, and it can be applied to any ReID-enabled trackers to make them faster, at least 2 to 5 times. So this is what LITE is, and it can be easily implemented. The implementation, as you saw, is very simple. Okay, now question is, we got suspicious, right? Interestingly, even though we are using non-trained, just off-the-shelf ReID features, we just got it from detection, it's performing same as other like a specialized ReID enabled trackers. So what we wanted to do is we wanted to evaluate the strengths of ReID components of each tracker. So this will be another contribution of Prime, right? The Prime allows us to like evaluate trackers, each factors which impacts their end result, because it's impacting, right? If you see here, this is really surprising. LITE is very simple, like it's just getting these features, the very simple features, rather than training separate CNN for identity distinction. We are just getting features from like an off-the-shelf YOLO model. How come it's working same as other like really specialized detectors? This is really surprising to us. And that's why, to find that out, we introduced ReID component evaluation methodology in Prime. What it does is, so this is a number of frames, and this is track, and this is a positive matches, right? Because this one track exists in multiple frames. So we match it against itself and compute the similarity of this positive match. And we compute it against negative matches, right? These are different persons. I apologize if you can't see it well, but this is a lady, and this is I think the two gentlemen here. And they are negative matches to this lady, right? They are not the same person. So this is what simply the ReID component evaluation is. And if you see here, we evaluated the deep sort's ReID component, and we evaluated strong sort, and OSNet corresponds to the deep sort and the bot sort. And we evaluated LITE paradigms, LITE's features. So what we have from here is that ideally this blue and the red should be separate from each other, right? If they are 100% separate, then we can 100% distinguish the positive and negative samples with appearance features. But this is not 100%, this is hard. So this overlap is actually contributes to error. And like if you see here, interesting thing is that in terms of AUC, so AUC is kind of a good metric to compare the strengths of the distinctive power of these representations. And like a LITE has 71, and which is better than deep sort, right? And strong sort and OSNet, they have a lower, much higher distinctive power. This is important because the deep sorts, the CNN model is trained to specifically distinguish the identities. Meanwhile, what we are using at LITE is actually not trained for distinguishing the identities. However, important point is the detector YOLO V8 we are using for LITE is more modern, more recent, meaning LITE can take advantage of research R&D in detection domain, right? When the new detector comes, there is no need to design new tracker. Like a LITE can directly benefit from that. And that's how it got a better representation power compared to deep sort, right? By just being implemented on top of detection with simple algorithm. And so far, we actually focused on the first layer of LITE. Now, but the first layer of the YOLO 8 architecture, but there are more layers, right? And we can extract this the activation map from any layer 1, layer 3, layer 5, right? Because this is what they are same. They have the same tensor shape, and of course the shape different, but the tensor dimension is same. Of course, it will go down as we go. When we keep computing, the speech size reduces, right? CNNs. So now, when we experimented these all layers, right? If you see, this is the conv layer 0, conv layer 1, and this is the specific layer to YOLO 8. This is kind of contribution of YOLO 8, and all the way to concat layer. And if you see AUC score of concat layer is highest, it makes sense, right? Because it's concatenating kind of multiple resolution representations from multiple resolutions, right? If they are in multiple resolutions, their abstraction layer, the features they are capturing are different. And when you concat them in a meaningful manner, which YOLO did, right? Because their network layer is trained for this concatenation to be meaningful. And obviously, intuitively, they perform better. So far, what we showed results was just with the layer, conv layer 0. But what I'm trying to say is you can apply LITE to any layer and any detector, like even YOLO 11. All right. Now, with after updates, this looks better for LITE, right? Because if you see here, the LITE wasn't looking well, but because it was layer 0. But if you improve, go to later layers, AUC also improves, and also the figure gets better, right? So this is kind of LITE's power, like you can use multiple layers representation. This is also good because depending on the scenario, you may need to choose which layer representation to use. Or you can do research and then devise your own algorithm, how to use each layers, how to fuse each layers scores. Okay, so now let's see insights from Prime. So Prime is like questions like prior publications. So this is, I know this is very bold and this is really big. However, at HumbleBee, as part of being advocate for the community and the business owners, we really would like people to focus on important things and be careful when we publish and use the whole idea, big picture when evaluating the methodologies, right? Because here, if you see, if I cut here at maybe confidence threshold close, like a little below 0.3, maybe this blue deep sort is best tracker. If I cut here, maybe this the strong sort is the best tracker. If I cut here, maybe this light deep sort is best tracker, right? And you will, the people in the field already know this is really the case, right? And that's why we have to use Prime and we have to care for the whole picture. And these small variations in ranking doesn't mean much because, as you can see, they can fluctuate when we change the confidence threshold. Okay, and another thing is here, each rectangle is lightened version of the ReID enabled trackers, right? So if you see here, deep sort, and when you lighten that deep sort, when you apply light, it will be rectangle. And every case, there is a FPS improvement, right? This is what I'm trying to show. Like every case, when you lighten, there will be significant FPS boost for your pipeline, for your solution. And there is little, there is almost no difference in terms of FOTA score, the accuracy. Of course, here, maybe this case, the lightened version of deep sort is losing accuracy, right? From maybe 37, it's coming to something below 36. But most of the case, it stays the same. And maybe at some case, it gets better as well, right? But of course, this should be considered almost same, these small variations. What's important is FPS. There is a significant FPS jump in any case. Another point from this figure is, if you see the figure on the left side, this column on the left side, this is MOT 17, and 0.05 is the confidence threshold, right? And this confidence threshold is actually not good for MOT 17 because when you increase the confidence threshold, HOTA score will increase. Can you see? They are shifting to right when you increase the confidence threshold. On the other hand, for MOT20, when you increase the confidence threshold, they are actually going down, right? The smaller confidence threshold is actually better. When you increase, it will actually go left, the HOTA scores. What it says is, like, this is another insight from Prime, and we were only able to do that because Prime treats whole tracking pipeline as holistic. And like, we really need to kind of care, and with a good engineering, custom solution, we can get way more from tracking. It's not just taking the solution, fitting it to problem. Rather, we have to understand the problem and adapt a solution for this problem. This is what the Prime suggests. So please recall, this is what we proposed before. What it says, I mean, we showed before, what it says is all trackers' performance varies when confidence threshold changes. That's why we have to find the optimal confidence threshold. But how? Because it depends on the scenario as well, right? For MOT17, maybe this is the optimal confidence threshold. But if you go to MOT20, maybe something small is optimal confidence threshold. Same thing goes for optimal input resolution. If you see here, maybe something like 1400 is optimal input resolution for MOT20, right? But if you go too small or even too large, still not good because HOTA suffers. So these are the factors affecting the final performance, right? And if you can see, they are affecting significantly. For example, here, based on what you use, you can either get this like a 20 HOTA score, or you can get as low as the 2, right? When you use the wrong confidence threshold. Also, because of this input resolution, this is much lower compared to others here, like a 45. Actually, sorry, this is on MOT17, but on MOT20, it was close to 24. But here it's like less than 20. So another insight Prime suggests is confidence of crops are higher for larger objects, right? What I mean by that is when you increase the resolution here, average confidence level per video is increasing. What that means is if it's too small, confidence of that detected crop is small. But if you increase the resolution, the scale gets bigger, right? The scale of the person. And then the confidence is also bigger. That's what this figure suggests, but only for MOT20. But for MOT17, this is true for certain videos, right? That is maybe true for purple, this purple one. But other videos, maybe not so true. Because the MOT17 contains relatively larger scale objects. And those large scale objects are maybe close to what the detector is trained on, COCO dataset. So that's why maybe it's not helping much for MOT17. So let's see this purple, and let's see more details about this. Purple one is the 10th sequence of MOT17. And if you see the 10th sequence of MOT17, its scale is like a much lower compared to other videos, right? And that's why, because its average scale height is lower, when you increase the resolution, this video is benefiting in terms of confidence. While others, they are already large, that's why maybe they are not benefiting much similar to this. On the other hand, for MOT20, although maybe this video's average height is maybe larger than this sequence, but they are much more denser. So this is another factor affecting the results, right? So if you see here, this is the density of the scene. This is number of people in one frame, right? For MOT20, yeah, some videos have a really huge, really large, like a number of people in one frame, like crowded scene. So this is another thing which is affecting, meaning equipped with these prime insights, now we know what kind of tracker we have to make. We have to make adaptive tracker, which can adapt to like a density, height, the resolution, the scene, and then based on this adaptive, it can adjust its confidence threshold, right? This is a really key, right? We saw confidence threshold is really affecting, depending on what kind of confidence threshold you choose, the HOTA score is changing. But if you adapt this confidence threshold for each track, which is in the being tracked, we should get the really better, most likely we will get the really better tracking results. Of course, this is a future research, and at HumbleBee, we are already actively researching on that. And we always welcome collaboration on R&D. We want to help community, and we want to collaborate as much as possible with the community, right? So yeah, this is another correlation between the confidence and the object scale, right? If you see when the scale, this x-axis is the object scale, when the scale is larger, the confidence is larger, right? This correlation shows that. And as I said, this is not always true, because it's not only the scale, it's also the density. This is another factor. And this is for MOT17, also the strong correlation between the scale and the confidence of detected objects. Okay, so now another insight Prime suggested is it really gave us kind of a question, right? Because when we evaluated components, when we isolated ReID components and evaluated them with our proposed methodology, we saw a really strong sort, and the OSNet is actually much better, right, in terms of their distinctive power. But the question is, why then there is no difference here, right? If you see here, so deep sort is almost same with the others, even though deep sort here is really poor in terms of distinctive power. This suggests a ReID capability gap, right? The tracking algorithms, they're matching score fusion algorithms are not exploiting ReID capabilities properly. So this is another future direction for research. We really need to investigate if ReID component is really needed, or maybe we are not exploiting them properly. If the ReID component is not needed, that means that we are just better off with pure motion. However, as we saw, the ReID components are really helping, they are helping us distinguish the positive and negative pairs. In this case, then why they are not showing up here in the final score, right? That's why, and this is, by the way, the true with all the previous literature, right? This is not I'm not the one who is showing the motion and ReID are almost same as a pure motion. You can investigate or follow these papers, and they also report a similar scores. There is no really difference when people add the ReID. There is no difference in terms of accuracy, but it slows down, obviously. Okay, so this is another insight Prime gave us during this research. Okay, now as a conclusion time, so we proposed LITE, right? It's a step forward in real-time multi-object tracking. It increased the speed 2 to 5 times without losing any accuracy. And evaluation framework Prime suggests us a really huge insights. For example, we can increase HOTA by 30% if we follow Prime insights and use a right sequence of decisions, actions when choosing the factors, rather in comparison to a worst case scenario, a random scenario. And there is also, we really need to care about tracker detector interaction. This is what Prime has shown. And also ReID components should be analyzed, right? Prime not only proposed a way to evaluate ReID component, but it raised a valid question of do we really need ReID components? Yeah, these are the conclusion and the contributions of this work. And if you are working on the R&D of multi-object tracking, video analytics, computer vision, we are always welcome to collaborate. Or if you have a business problem on the multi-object tracking and like a kind of optimization of your vision systems, video analytics, we are always happy to help you at HumbleBeeAI.